Okay, we're going to start our analysis with graphing and limits by looking at rational function that we've dealt with before, f of x 1 over x minus 1. We've seen that in pre-cal and college algebra. So we'll just take a look at this function and how we might deal with that. Notice that a good practice here is I've written the function here and kind of broken my page up into kind of halves and quarters, I guess. So I've got my graph over here to the right, my function. I'm going to do my analysis going down the left side of the page. And to match up and make my life easy, I'm going to go ahead and put the table immediately under the function, like this. Okay. And to help myself as well, I'm going to pull up a calculator. I'm going to be using this time around a TI-84, a little emulator here you can see. And that calculator, I'm going to be using some values in it, and we'll take a look at that, and we'll clear that up here. Just going to quit, and I'm going to do a reset of my calculator, second memory. 7, 1, 2. Totally reset my calculator to use here. We got that going. And I'm going to go to y equals on my calculator. I'm going to go ahead and do 1 divided by bracket x minus 1. Put that in my calculator. I'm going to use table to help me out here. Notice the table is in auto right now, so I'm going to change that as well. I'm going to go second table set, and I'm going to use my little arrow here and put my independent variable in ASK. So I've done a couple of things there. So I go to the table here and I can do that. That's just to help me out. I mean, I'm going to do it down the side as well. And I'm going to look at some clear values here that I want to deal with. I'm going to deal with like 0, 1, 2, and 3 as some just go-to values of my function, and I can do them by hand. That's not going to be a hard thing to do. F of 0 is 0 minus 1. That's going to be 1 over minus 1 or minus 1. I can put that on my graph here. Notice my graph has an arrow and a label. That's also a go-to thing. Don't forget that. My y-axis is labeled and it has an arrow, and the 0, 0 is the origin. So kind of good practice things. F of 1, I'll give that a shot. 1 minus 1. Notice I get here 1 over 0. This is undefined. So I see that I have one undefined value. I'll just write that UND. And on my graph, I'm going to go ahead and at that 1, and I'm just going to put this dotted line up here. And we know from previous classes, this is very likely to be a vertical asymptote. So we'll take a look at that, do a little analysis of that later. I can do f of 2, and I can pull that down. So let's see, f of 2 is going to be straightforward, 1 over 2 minus 1, which is 1 over 2, which is 1/2. A little redundant there. And then f of 3, I'll do that. 1 over 3 minus, whoops, sorry, I did that wrong. That was 1 over 1. That should be 1, not 1/2. You know, try to be careful here. 1 over 3 minus 1, that is going to be 1 over 2, or 1/2 for the f of 3. F of 4, I'll get 1 over 4 minus 1, or 1/3. So 3 is 1/2, 4 will be 1/3. So I kind of get that amount. Let's see, at 2, I get 1. At 3, I get a half. And at 4, I get a third. So that's just giving us that shape of that graph, and we can keep going with that and playing with that. And I can use my calculator to help myself out here. So I'm going to go ahead and repeat that on the calculator, make our lives a little easier. There's a 0, there's the 1. My calculator puts in error because that's what it does for undefined. 2, 3, 4. Notice the calculator helps me out. It does these calculations really well for me and quickly. It does not give me fractions though, it only gives me decimals, but that's what we got. 5, I can go through this. And I can see, we get that feeling that we get before when we played with this kind of function, is as we go to the right, these values are going to have a tendency to get smaller. And a way we would write that would be something like we wrote before. We would say as x goes to the right. That's not very mathematically accurate, so we might actually add that something to that. So we'll do a new page here. We'll maybe say something a little more accurate, like as x goes. And when we say to the right, we mean as x goes to, if you remember, larger numbers like positive infinity. So we might say as x goes to positive infinity, that implies that y is going to, well, we're not sure, but we can play with our calculator here and see. And now I'm going to use my go-to values. And my go-to values I can use either in a table, which are 10, 100, 1000. Those are kind of my go-to values. I can do f of those. So f of 10 is going to be 1 over 10 minus 1, which is 1 over 9. If I do f of 100, I'm going to get 1 over 100 minus 1, which is 1 over 99. And then I can do f of 1000. And I do that, that'll be 1 over 1000 minus 1 over 1 over 999. We can make our lives simple and do that on the calculator and simply get 10, 100, and 1000. And you see those values are going to be small, 0.1, 0.01, 0.01. So in my table, 0.1, 0.01, 0.001. And we see as these values get bigger, as x goes towards infinity, we see easily that y is going towards 0. So that kind of helps us with our first kind of behavior here going on in my graph, that what we're actually seeing here is, and we'll make this a little more obvious with trying to make this obvious with a color. Oh, we'll just do it. There we go. We'll do it in red here. So as I draw that here, I get that kind of behavior going here. So as x goes to the right, we get that behavior going to the right. As x gets smaller, y goes towards 0. So right, this x gets larger, y goes to 0. So that actually describes the behavior that I'm looking for. So now I'm going to take a look at the behavior over here, and we can do that again by playing with the calculator. In this case, we're going to go ahead and choose, just get that over here out of the way. We're going to go ahead and choose something like, well, this time we actually want to approach 1. And again, we want to approach 1 from the right side. So we would do something like, 1.5, maybe 1 1/3, but I'm going to do 1 1/10, or 1.1, 1 100th, or 1.01, and then, of course, 1 1,000th, which is 1.001. So on the calculator, we'll do that sort of thing. So we'll do 1.1, 1.01, 1.001. And I see here, obviously what I'm getting here is I get closer, these values are getting larger. So this is going to go to 10, 100, 1000. And remember, over at 1, it's undefined. So as x approaches 1, and we're going to be really specific about how we're going to write this. So I'm going to use a superscript with a plus sign, and that means really from the right, or the right-hand side. So as x approaches 1 from the right-hand side, y is getting bigger and bigger, 10, 100, 1000. This is actually approaching plus infinity. So this is giving us that kind of behavior that we were looking for as well in the graph. And we go back to here, we can see that graph right, whoops, sorry, drew that badly. We're graphing that here as it approaches 1, this is going to infinity. And this was actually in pre-calculus. This was our definition of a vertical asymptote. That's exactly what this is. This is by definition with a vertical asymptote. So this would be x has a vertical asymptote at x equals 1, right? That's by definition. And if we look back up here, what we were saying up here is this our definition of a horizontal asymptote. As x approaches infinity, y approaches 0. So we both have that horizontal asymptote, which I can draw as this behavior here, and the behavior here that we got from over here, this I could draw as this behavior here. So that behavior is reflected in that little graph that we had. Notice we have all this work, all this algebraic work that backs up to that shape of the graph. Okay. So, and we can do a similar thing and play with this over here, and we're going to see that this graph is going to have a similar behavior here. And notice that at 1, if I had drawn this a little better, this would have been my, let's see, whoops, we got to go back here and redraw that. So we saw that y was approaching 0, so this must be approaching 0 here. Be careful about that. Our horizontal asymptote is actually y is equal to 0. Our vertical asymptote right here is actually going to be x equals 1. The vertical line, x equals 1, this line here, that's our vertical asymptote, and the x-axis here actually is serving as our horizontal asymptote. We can actually take a peek at the graph. I mean, it was always there on our calculator, and see that the graph does get graph like that. It gives our window on the TI-84 isn't so bad, and it gives us that kind of behavior, but the best explanation for the behavior is over here on the right. So this is our two approaches here using our pre-cal and algebra kind of thing. So what we're going to do with limits. So what we're going to talk about with limits, well, the concept of a limit really isn't far from what we're talking about here. We discussed there as x approached, for example, 1 from the right. And we said that y goes to, in that case, plus infinity. And the other one, which was interesting, as we said, as x went to, sorry, terrible looking x there. As x approached positive infinity, y goes to 0. So these two kinds of things we can actually express in the same way. We can actually say, for example, here, as x goes to 1 of f of x, in this case, we can actually express that limit as plus infinity. And notice we are very specific with the way we write this. We're writing the same statement we wrote here as x approaches 1 plus of f of x. And we can actually write that alternatively. We can say the limit as x approaches 1 plus of 1 over x minus 1 as a function. Notice we put it in the brackets is the same thing, right? And how do we actually work that out? We can see that that limit is the same thing that we did before. We actually are looking at the value 1. We are approaching the value 1. Now the value at 1 is undefined, but as we approach the 1, and we said that before, the 1.1, 1.01, the value is like 1.001, we saw that this was 10, 100, 1000. So this limit is really just expressing that. This part here on the right, this part here we see that's expressing the y. So as x approaches 1 plus, y approaches infinity plus. So that's, in a basic way, that is what the limit statement is saying. The limit statement is really saying that kind of thing. And we can actually expand that a little bit too, because in our case, we might have been working, for example, and looking at what would happen at another value. So we looked at the horizontal and vertical asymptotes, and notice we ended up expressing those as limits, which we will define in a little bit. But the short point is that we could also have talked about the limit as x approached another value. Let's say x approaches the value 2, and we'll say either from the right or the left. We'll say from the right of 1 over x minus 1, or f of x. And remember our graph, if we looked at that graphically, so we'll look at 2, and here's 1 with our asymptote. We know the graph did this kind of behavior. It goes down. Whoops, terrible drawing there. We'll try that again. And what was particular of the value 2 when we looked at our graph was that it actually went through the value 1. So in this case, as we were looking at it, if I took the x values and the y values, and I actually looked at the value 2, and I did something like 2.1, 2.01, 2.001, and let's do the calculator to make our lives nice and simple. So I'm going to go to table again to get our calculator to do our work for us. That's what we like. We'll go up here and we'll do 2. Well, this time notice that value at 2 is 1. If we go here and we do 2.1, 2.01, 2.001, we see that the values are 0.9, whoops. Yep, that's right. So 0.9, this should be, oh, sorry, I'm missing on you that 2.01, missed the decimal there, 0.99 and then 0.999. So here we get 0.9 approximately, 0.99 approximately, and 0.999 approximately. So we see as x approaches 2 from the right, y is approaching the value 1. So in this case, it's a nice, easy value. And we see as x approaches a certain value from the right, it approaches 1. And that's exactly what it's doing on the graph. As x approaches 2 from the right, the y value is approaching 1. And notice it's actually approaching 1 specifically. It's approaching 1 from underneath. Sometimes we can actually notate that in this case we see that it's 1 with a negative sign. It's not necessary, but it does give you an idea that it's approaching 1 from the bottom. It's actually poorly put there, so let's put that over here like that. There you go. And we could actually do the limit the other way and say, wow, let's see what happens when it approaches f of x on the left. And we will note, and we'll see easily, that that will approach 1 from the top, right? So those would be values a little smaller than 2. So, or smaller, yes, smaller than 2, so something like 1.9. Whoops, try that again. 1.9, 1.99, and then 1.999. And notice these values are getting closer and closer to 1. But from the top, these values are bigger, a little smaller and smaller. And that's exactly what's going on when the graph comes down. It's coming down to that value. So these values are approaching both from the top and bottom. And notice that makes a very, we'll use the word connected kind of thing. It's very connected because as we do the dots going to 1 at the value 2, it's very connected and leading to that. We have a better word than the word connected. We'll use this word continuous. And actually, we've talked about this continuous right here. And this, the two limits, are going to help me define continuity. Notice we've been talking about left-sided and right-sided limits in general, what we could have just done is just say we've got a single limit. In this case, we do have that. We have the limit as x generally approaches the value 2 from left and right of f of x, or from of x 1 over x minus 1. Notice I keep putting these brackets in good practice so I don't lose anything. This is going to be the value 1. Notice this is a great way of talking about the limit. And notice this limit exists. And it exists particularly because that limit is also equal to the limit as the value approaches 2 from the left of f of x. And it's also equal to the value as the limit approaches this value from the right of f of x. These both equal the limit at the value 1. So the left-hand side limit is equal to the right-hand side. That's going to be important to us later on as well. This gives you a basic idea about limits and graphing and some analysis, and we'll do a few more examples later on just to give you a start.